Hello everyone, this is Greg from ChemCore. In this video, we're going to be going over the acids and base worksheet. This is the first video of Unit 3, and if you haven't watched the topic video, make sure to go check in the description and watch that topic video. And if you haven't seen this worksheet, it's also in the description below. Now, the first question on this worksheet is asking us, what is the conjugate base for each of the following acids? And so what we're really asking to do is, well, we have kind of an acid, and what is going to be the conjugate base for this acid? In other words, kind of the easiest way to think about it is when it loses one of those protons, what is it going to become? And we can kind of use the Bronsted-Lowry definition for this. And if you don't remember what the Bronsted-Lowry theory is, I know they get confusing. You can also go check in the description. That topic video includes kind of breaking down the different theories we have for acids and bases. Now, the first couple problems, NH3. Now, NH3 usually is not an acid. It's actually a base, but it doesn't matter, right? We're just asked what is the conjugate base. And so if we lose a proton, we're going to become NH2. But remember that losing a proton doesn't just mean you lose a proton, you also get an extra lone pair. And so this nitrogen already had a lone pair. Now it has an extra one, meaning now that it has a negative formal charge, right? Nitrogen likes 3 bonds. It has less than that, so it has a negative formal charge. If you're unfamiliar with that little trick that I just used, Unit 1, there is a video on formal charge and Lewis structures, and I use a little trick there to really quickly calculate formal charges. Now, water, really, I guess, canonic example to use for acids and bases. Now, if water loses a proton, it becomes OH, but it also kind of gains a lone pair. It used to have 2 lone pairs, now it has 3 lone pairs, and it ends up with a negative formal charge. H2 is a weird one. H2 will just lose one of the hydrogens and then get left with an extra lone pair. And so you end up having this kind of negative hydrogen, right? Something like that. Now in the next problem, we'll lose one of the protons on this carbon. And this actually is pretty difficult, and the reason why it's pretty difficult we'll explain in a future video. And it also gains a lone pair because of that and gets a negative charge. Now, in the next problem, you might be confused, well, which proton do I take? This concept is going to be explained a little later, but it's going to be this proton. Just remember, for now, if you have 2 options, and one of the options is a proton from carbon versus a proton from literally anything else, you're taking the proton from literally anything else. A carbon is probably going to be one of the last things that you'll take a proton away, unless there's no other options, like in the previous problem. And so we're going to take the proton away from that oxygen, leaving it with an extra lone pair, and it now has a negative formal charge. Now this H3O+, this is the hydronium ion. If we lose a proton, we end up just as H2O with 2 lone pairs and a neutral formal charge. H2PO4, if we lose one of those protons, we just become HPO4. And now we already had a negative charge, and so we can kind of assume that we'll have now 2 minus. And then the next problem, HCN, we'll be left with just CN, and then we'll have a negative charge right on that carbon because that's where the hydrogen is attached. And now the last problem, you have these 2 hydrogens, just choose any one you want. I'll choose the one from the right. And so I'll write out the whole thing. We're left with an extra lone pair right over here, and we get a negative formal charge. Next, we're asked, what is the conjugate acid for each of the following bases? And so really what we're trying to do is we get a base, and we're saying, okay, what is going to become the conjugate acid? But when? Well, when we get an extra proton. And so this method of kind of determining is, again, according to the Bronsted-Lowry definition. And this is why I really like Bronsted-Lowry. We're going to be using Bronsted-Lowry mostly in organic chemistry to describe a lot of movements and a lot of acid-base reactions when we combine with other types of reactions. So in general, when we get an extra proton, we're going to lose one of the extra lone pairs. And so we're probably going to bring up the charge. Now HSO4 is going to become H2SO4. This is actually sulfuric acid, one of your strong acids. And since it had a negative charge before, it now is neutral. H2O, it will become H3O. And since we gained an extra proton, it becomes positive. And CH3NH2 what I want you guys to realize is, again, carbon probably won't gain an extra proton because it cannot handle more than 4 bonds. And so the proton's probably going to go to the nitrogen, meaning that we end up with CH3, NH3, and then the nitrogen has a positive formal charge. You can write positive at the end. I'm just writing positive over here to specify that it's the actual nitrogen that has it. Now NH2, kind of the conjugate base from the previous problem, if we gain that proton back, we'll just become ammonia, right? Neutral. Now CH3, CH2, we're going to gain that proton all the way at the end, and we're going to become fully neutral again. This is going to become CH3, CO2H. I want you guys to realize, well, how did you decide that the H goes here? I can't put it on here because then we'll have more than 4 bonds. I can't put it on this carbon because, again, we'll have more than 4 bonds. I can put it on the end. And realize this becomes your formula for general carboxylic acids, right? CO2H or COOH. Now, the next 3 problems, we have F minus, and so we'll gain that proton, just become HF. OH minus is your hydroxide ion. If we gain that proton back, we'll just become H2O. And obviously water is neutral. And NH3, kind of from this problem, if we gain another proton, we become NH4, which is the ammonium ion. Now in problem 3, I wrote out a bunch of acid and base reactions, and I feel like this is really good repetitive practice to get used to labeling your acids, your base, and then your conjugate acid and your conjugate base. And so just to review, your acid will become your conjugate base, and your base will become your conjugate acid. And so from before, hopefully we're now kind of familiar with the fact that the acid will lose a proton while the base gains a proton. And so when I look and I kind of examine an acid-base reaction, I don't like to look at one side. I like to look at the 2 sides kind of as a unit, right? You can't really determine who gained the acid if you don't look at what happened after. So for example, in the first problem, I can look at NH3. This caught my eye, right? But which did it act as an acid or a base? I look at the end and I notice that it's now NH4, meaning that we gained a proton. And so I know that NH3 here acted as a base. And obviously the NH4 after is going to be your conjugate acid. I'm not writing out the full word for conjugate. It's a little too long, so I'll just leave it as conj, but realize it's just conjugate. Now, obviously, if this one is your base, that means this one has to be your acid. And then the other one must be your conjugate base. And just to review what this means, if you were to look at it the other way, I know we usually read English from left to right, but imagine we read it from right to left, you would then think, oh, now nitrogen, this NH4, acts as the acid, right? It becomes NH3. And this CO3 acts as the base, right? It gains that proton. That's what conjugate means. If we had this reversible reaction, what would then be the acid and base? Because a lot of these acid-base reactions, unless you have strong bases and strong acids, are reversible, right? Including this reaction in front of us. The next problem, sometimes you'd be able to figure out what's the acid and what's the base without even looking at the end. HCl, you should realize, is a strong acid. So no matter what the products are, it's always going to be the acid. And clearly we lost a proton, became Cl, so that's correct. And so this will be your conjugate base. Now your H2O had to be the base, right? Because we gained that proton. And so here we are the conjugate acid. In the next problem, I see that this big compound loses a proton and becomes negatively charged, so I know that this is my acid. And the end product must be my conjugate base, while the water gained a proton, so I know that it's the base. And the hydronium ion is the conjugate acid. Now the next problem, I see HOCl. This becomes ClO-, so we know that we lost a proton. It was an acid. And the end product must be the conjugate base. And now ammonia gained a proton, meaning that this is the base, and ammonium ion is the conjugate acid. And now most situations, ammonia will be the base for reasons that we actually will explain in a future video, unless combined with 3 kind of specific groups of compounds. In that case, it might act as the acid. Now H2SO4, you don't even have to look at the end product, and OH minus, you don't have to look at the end product. I know that H2SO4 is sulfuric acid. This is a strong acid, and so virtually all the time it's always going to be the acid, and OH minus is your canonic base, right? That is the hydroxide ion. And so when it loses a proton, it becomes a conjugate base. This is your sulfuric acid, and then water becomes your conjugate acid. Now, CO3 minus becomes HCO3, so we gained a proton, meaning I know that it's my base, and the end product needs to be your conjugate acid. And then H2O, we lost the proton, and so I know that it's my acid, and I know that the hydroxide is my conjugate base. NH4 plus is my ammonium ion, and so if I look to my right, again, we lose that proton, meaning that the ammonium ion is my acid, and the ammonia is my conjugate base, and my hydroxide ion is your canonic base. And so when we gain that proton, we become H2O, meaning that H2O is now our conjugate acid. And now the next problem, kind of interesting looking reaction. We have both carboxylic acids kind of in equilibrium with each other, reacting with each other. And so I see this HCOOH becoming HCO minus. Make sure to not get confused. This is your acid. And then the end product is going to be your conjugate base. And then this guy over here is your base. And the end product will be the conjugate acid. Now HCN becomes CN minus. And so I know that this acts as my acid. And the end product will be the conjugate base. And now water must act as the acid, and it does. It gains a proton, meaning that the hydronium ion is your conjugate acid. Now in the next problem, we have this really confusing compound. It gains a proton on the nitrogen, meaning that I know it's my base, and that end product must be the conjugate acid. While this H2O gave away a proton, so I know that it's my acid, and the hydroxide must be the conjugate base. And now this reaction with two waters, this is actually displaying the autoionization of water. When water ionizes itself, this is actually what happens and how we get a bunch of calculations for Kw and other things that you might remember from general chemistry. We don't really focus on that here. Now it's kind of difficult to tell which one is the acid, which one is the base, because this one could become this one or this one could become this one, but we're just going to pretend left and right is the same. And so this water became this hydronium ion, and so I know that this was my base. And so the hydronium ion must be my conjugate acid. While this water gave away a proton, so I know it's my acid. And this is my conjugate base. The next problem, we have this HSO4 that continued to give away another proton, so I know it's my acid. And the corresponding one must be the conjugate base. And the water gained a proton, so I know it's my base. And the corresponding must be the conjugate acid. And then the next two problems, we have OH minus and hydronium ion. This is kind of the backwards reaction from the one we had above. Hydronium ion, or hydroxide ion, that's the one I'm pointing to, will gain a proton, meaning that it's my base. And this one must become our conjugate acid. While the hydronium ion gave away that proton, so I know it's my acid. And the corresponding product is my conjugate base. And in the last problem, I have ammonia gains a proton, becomes ammonium ion, and so I know it's my base. This is my conjugate acid. And then water gave away that proton, so I know it's my acid. And the corresponding is the conjugate base. Now, with problem 4, we begin our multiple choice problems. The first problem is asking which of the following is not a conjugate acid, conjugate base pair in that order. And so we're kind of looking specifically. The first one must be a conjugate acid. We're literally able to give away a proton, while the conjugate base pair must be willing to accept. And now a clue that maybe this one could be positively charged, while the conjugate base might be negatively charged. It doesn't have to be, right? The conjugate acid could be positive and this one, but it could be a little clue, right? Could be a nice little rule of thumb that we use. Now, the first problem, we see H3PO4. This is phosphoric acid. And if it loses a proton, it becomes this, which is exactly what we're looking for. And so this is, we can cross it out because it is a conjugate acid, conjugate base pair. Now, in the next problem, we have HBF4, and we lose that proton and become BF4. And so this is kind of willing to accept. This one is willing to give away. And so we can also eliminate this problem, or this answer choice. CH3, CH2OH, we lose this proton right over here, and we become a negatively charged oxygen, meaning that this is also the conjugate acid, conjugate base pair. H3O plus, or hydronium ion, can lose this proton and become water. And so I know that this is also a correct pair. While the last one, you're looking at it, and it's like, we went from one hydrogen to two hydrogens. So isn't this the conjugate base, and this is the conjugate acid pair? Yeah, I mean, it is. It's flipped. And so this is not this doesn't follow this kind of what they're saying, conjugate acid, conjugate base. We're saying conjugate base, conjugate acid. And so this would be the correct answer. Now, the next problem is asking a conjugate base of sulfuric acid is, well, the first job is, well, what is sulfuric acid? Sulfuric acid is a strong acid, H2SO4. And the conjugate base is when H2SO4 acts as an acid, it will lose one of the protons, becoming HSO4 negatively charged. And so when this is the acid, this is the conjugate base, meaning that the correct answer is C. Problem 6, which of the following is not a Bronsted-Lowry acid? We're basically asking which one is not able to give away proton. Now, H2O definitely can give away a proton and basically become OH minus, right? We've seen that a lot. And so this is a Bronsted-Lowry acid. We're going to skip this problem because even though I do see hydrogens on the carbon, that thing I told you before that the carbons really won't want to lose any of the hydrogens is exactly true. We don't want it to become a carbocation or carboanion. And so we maybe skip this one. We'll see if we have a better option. But NH4 plus, this is the ammonium ion. And so if we lose that proton, we'll just become ammonia, right? So this is definitely can act as that Bronsted-Lowry acid. Now D is a carboxylic acid. This should be telling you that it could act as a Bronsted-Lowry acid. We'll just become CH3, CO2 minus. And the last one, again, you're asking, but why can this one act as an acid? Because we have this hydrogen that's on a triple bonded carbon. This is going to make more sense a little bit in a later video when you watch the video on ARIO, or acid-base strength. But this could become HC minus. And so the only one that is not a Bronsted-Lowry acid is answer choice B. The next problem is asking us, what is the conjugate base of ethanol? So when ethanol acts as an acid, what does it become? Well, ethanol is CH3, CH2, OH, right? 2 carbons. And so when it acts as an acid, it ends up donating a proton and becoming CH3, CH2O minus, which is the conjugate base. And so the correct answer choice is A. Now, problem 8, which are the Bronsted-Lowry bases? Remember that they're not telling you which one is the Bronsted-Lowry base in the forward reaction. They're telling us in general. And so that previous worksheet that we had of really repetitive kind of labeling acids and bases and conjugate acids and bases is going to be really helpful. From the left side, which one gains the proton? Well, the PO4, right? And so this is our base looking from the left. But if we read from right to left, which one gained the proton? Well, OH minus because it becomes H2O. And so from the right, this is our base. And so the correct answer choice is B, PO4 3 minus and OH minus. Now, number 9 is asking us, according to the Lewis definition, a base is, well, this is a straight definition question. If you don't remember this, rewatch the topic video. It's in the description below. I go into depth describing each Lewis and Arrhenius and Bronsted-Lowry. And so according to the Lewis definition, a base is an electron pair donor, while an acid is an electron pair acceptor. Number 10, which of the following is not a Lewis base? Now, a really good way to determine whether something is a Lewis base is to remember its definition. It's an electron pair donor, right? Electron donor, which means it must have a lone pair available. And so if we were to draw them all out, which one does not have a lone pair to give? Well, NH3 will look like something like this. I hope you guys are pretty good with constructing your Lewis structures at this point. It has that lone pair, meaning that it definitely is able to act as a Lewis base. H minus, it can only be H minus if it has an extra lone pair. It gained that lone pair, right? And so we have this lone pair, meaning that it can definitely donate and act as a Lewis base. Now BF3, I actually talked about this in Unit 1. BF3 is a really popular example for Lewis structures and formal charges because a lot of students end up drawing it like this. This is actually wrong, right? BF3 has 3 bonds, but no lone pairs, and so it kind of looks like a nitrogen atom, but not really, right? It's more trigonal planar, while a nitrogen atom in this problem will be trigonal pyramidal. And so since it has no lone pair, we can kind of look at answer choice C as being not a Lewis base because it has no lone pair to donate. Now H2O, I don't think I have to redraw the Lewis structure of H2O at this point. It definitely has, well, 2 lone pairs to donate, and so it could definitely act as a Lewis base. And H3C minus, well, if we drew this out, remember that a carb anion can only be a carb anion if it has 3 bonds and a lone pair. And so this lone pair makes it a Lewis base. And so our correct answer choice is C. 11 is asking which of the following is a Lewis acid. And so remember that your Lewis acid definition is that it's an electron acceptor, meaning that it could possibly accept another lone pair. And so we have to find out which one of these doesn't have the lone pairs and still could kind of get an extra lone pair. Now, first off, if we draw the Lewis structure for H3O, we would understand that we have this kind of lone pair, but realize that oxygen can get an extra lone pair, right? It can have up to 2 lone pairs, even up to 3 lone pairs. And so it can definitely act as a Lewis acid if it loses one of these bonds. And so this is definitely a Lewis acid. Let's mark this and keep going. Now BF3, it's a structure that we draw in the previous problem. Now BF3 by itself has no lone pairs, meaning that it can't act as a Lewis base. But can it act as a Lewis acid? Well, probably it can, right? What's stopping it from getting an extra lone pair? And so this is definitely a Lewis acid, right? It can definitely accept another electron pair. Now NF3, we have this lone pair right over here. Now realize that what we're saying is that this guy has to be able to accept another electron pair. But it already has an electron. Where is the other electron going to go? Is it going to lose one of these bonds? It kind of can't, right? It can't lose one of these fluorines. It just can't just break it. It's not a hydrogen. And so this actually can't act as a Lewis acid. And answer choice D, OH minus, would look something like this. So we already have 3 lone pairs in the oxygen. It can't get an extra one, right? It definitely will not lose this hydrogen. And so it also cannot act as a Lewis acid. And so our answer choices are both A and B, meaning that more than one of these choices, so E. Question 12, which of these is not a Lewis acid? And so again, when I see Lewis, the first thing I'm going to do is draw it out. It's also notable to remember that a Lewis acid is going to be an electron acceptor, meaning that we should be able to kind of get another lone pair when there isn't one. And so aluminum trichloride is going to look like this. It actually looks a lot like boron. And we don't have any lone pairs in the aluminum, meaning that we should be able to accept another lone pair. And so this is definitely a Lewis acid, so we can eliminate A. H3O, we already talked about this in the previous example. We have this lone pair, but if we were to break one of these bonds, we could get an extra lone pair, meaning that it definitely is a Lewis acid. FeCl3, we can't really draw a Lewis structure for FeCl3, but realize, because it's ionic, we definitely could accept some lone pairs on the iron, right? It's not covalent. It can definitely just grab some more electrons. And so iron trichloride, or iron 3 chloride, can definitely accept some more electrons. Now SO3 would look something like this. And so when I look at this compound, I see a lot of options, right? I see this lone pair. I see this double bond, meaning that we can definitely break one of these double bonds and get another lone pair on the sulfur, right? This is actually can act as a resonance structure or even as a Lewis acid. The last problem, however, is CH4 H10, meaning that it's literally just butane. And so, quick reminder, carbons that are single bonded will never, ever lose hydrogens or gain hydrogens. It just doesn't happen. They could lose something that we're going to talk about in Unit 6 when we start talking about leaving groups. But in general, sp3 hybridized carbons or single bonded carbons will never, ever, ever either donate or gain protons. They won't gain protons because they can't get an extra bond. They'll then have 5 bonds. It breaks all kinds of rules. But they won't lose protons because then that leaves them with an extra lone pair, which they really, really don't like. They're kind of weird. And so they will never, ever act as Lewis acids. They won't act as any acids, actually. The last problem on this page, again, we're looking for which one is not a Lewis acid. So let's remind ourselves that a Lewis acid is an electron acceptor. Best way to figure this out, let's draw it out. And so aluminum will have these 3 bromines attached to it, kind of very similar to a previous problem in the right over here. And so reminder, aluminum can definitely gain an extra lone pair, right? It can become this kind of compound. And so this is definitely can act as a Lewis acid. BCl3, boron trichloride, actually looks really, really similar. And so boron can also accept a lone pair. So it can also act as a Lewis acid. PH3P is just phenyl, right? We have 3 phenyl groups on this phosphorus. And we already have a lone pair. So this kind of looks a lot like nitrogen, where we won't be able to get another lone pair. We can't just break one of these bonds, right? It's phenyl, it's not hydrogen. And so this definitely cannot act as a Lewis acid. But what is the last one? Well, D is actually deuterium. And if you're not sure about what this is, I have another video in this unit separately talking about deuterium and tritium. It's a really short video. I really suggest to go watch that. And so if you watch that video, you'll realize deuterium is just a hydrogen isotope where it has an extra neutron, so it kind of becomes do or dos, whatever, that's where the name comes from. And so realize that H can definitely accept another lone pair and become minus. We've actually seen that problem before. And so should deuterium. If you watch that video, you realize I told you guys deuterium and tritium act exactly as hydrogen for all your reasons. They're just kind of good for labeling and figuring out how the reactions work. And so D can actually definitely act as a Lewis acid. And so E is definitely wrong too, meaning that C is the only choice that cannot act as a Lewis acid. Question 14, we're looking for the species that is a carbon-based Lewis acid. And so I told you guys before that single bonded carbons will pretty much never, ever, ever either act as acids or bases. So we can really eliminate A. Now it's also notable to remember that the acid will act as an electron acceptor. So we're probably looking for something that can accept another lone pair. Now D and E, I don't even know what E is. I know what E is. You guys don't know what E is. You've never seen this unpaired electron before. There's actually a radical, something we talk about in chapter 10. But realize that it really doesn't matter. Because of these extra electrons, they definitely won't want to get another lone pair. But C already has this plus charge. It already lost kind of the proton. So why can't it gain electrons, and become D? Will this be kind of favorable, or will this happen in nature a lot? No, this will not happen in nature a lot, or not to the point that we can see. But theoretically, on paper, this can definitely happen. Which pair of species are both bases in the following reaction? Again, we're looking to label both sides of the reaction. Now, from the left, I realize this is HCN donates a proton, so this is my acid. Now, the water will gain a proton, meaning that this is my base. But if I read it from right to left, this cyanide, the cyanide ion, gains a proton. And so it's really we can name it as our base, but it's really our conjugate base. While the hydronium actually loses a proton. And so here it acts as the conjugate acid, or the acid from the right side. And so the species that act as bases are the cyanide ion and the water, meaning that our answer choice is A. And the last problem on this worksheet, which of these is not a true statement? And so answer choice A, all Lewis bases are also Bronsted-Lowry bases. You might be thinking, well, they're not related. They actually are related in a way. If you remember that Bronsted-Lowry were breaking the bond between the central atom and the proton, well, what happens, right? We gain a electron pair. Well, if we're a Bronsted-Lowry base, we're going to be accepting a proton. So kind of doing the opposite. The only way we can accept a proton is if we donate one of the electrons. And so this is actually a true statement. Answer choice B, all Lewis acids all contain hydrogen. This is actually not true. Lewis acids do not have anything to do with hydrogen. They have to do with lone pairs. And so Lewis acids just have to be willing to accept a lone pair. They don't have to have hydrogen, right? We've seen problems in the past in this worksheet that there were Lewis acids that actually did not have hydrogen many, many times, like aluminum trichloride, boron trichloride. And so this is actually not a true statement, but let's read through the rest and understand why they are true. All Bronsted-Lowry acids contain hydrogen. Well, yeah, that has to be, right? A Bronsted-Lowry acid has to be willing to donate a hydrogen. And so if it doesn't have a hydrogen, what hydrogen can it donate? Answer choice D is saying all Lewis acids are electron deficient. Lewis acids can accept an electron, meaning that they're missing electrons, right? They're missing some of those electrons or deficient in electrons. And so we can answer with answer choice D. And so we actually go into a little bit of depth on this answer choice in a future video in this unit. And by the time you're watching this video, it should be out, going into depth about Lewis acids and bases. And our last answer choice, according to the Bronsted-Lowry theory, water is both an acid and a base. It definitely is, right? We've seen that example earlier in the worksheet. Water can accept a proton and become H3O plus or act as an acid, while it can also donate a proton and become OH minus or act as a base. And so water can both act as an acid and base. This concludes our worksheet on the acids and bases topic. If you're unfamiliar or not sure with these concepts, go back into the description and watch the topic video. I'm sure it will help you out a lot. And maybe retry this worksheet. Everything is always free. And I'll see you guys in the next video.